All right, so in the last video, I was showing you how to do inference for one proportion. Now we're going to do the same thing for one mean. And in this case, we're going to use that number of hours worked last week as our statistic. And I'd like you to see if you can compute that point estimate. So pause the video and see if you can remember how to find that mean. And now I'll do it. So I'll do the mean of tilde number of hours worked last week, comma data equals GSS. If I control enter, our point estimate is 41.3, maybe we'll estimate. And we could compute the standard error by hand. So here's our standard error formula. And there's one more thing we need to know, and that's the standard deviation. And we can find the standard deviation the same way. Number of hours worked last week, comma data is equal to GSS, and it's 14.5. So I'll do 14.5 divided by SQRT parentheses of the 2348. And then our standard error is about 0.3. And then the last thing we need is a critical t-value to finish out our confidence interval. With the t distribution, you can't have those critical values memorized because they depend on the degrees of freedom. So we'll compute our critical t-value using this function qt. Again, I use 0.975 here, and I put in the degrees of freedom are n minus 1, 23, 47. So that's my critical value. It's basically 1.96. So the t distribution converges to the normal as the degrees of freedom get larger. And then we could compute our confidence interval by hand. So we've got our, 41.28, 1.96, and our basically 0.3. And we could find our confidence interval. And I could say I am 95% confident the true mean number of hours worked per week is between 40.7 and 47. Oh, shouldn't be 47. That's really big. I have a typo here. It should be 0.3. There we go. And 41.9, basically, hours. And again, we could ask R to do it for us with the t.test function. It uses the formula syntax. And this would give us some information, including this 95% confidence interval, which is very similar to the one that we just found, although maybe a little bit off. Again, there's like some rounding stuff and some distribution stuff. And we could do the same thing for the hypothesis test. So if our null hypothesis was that the mean was equal to 40, and our alternative is that it's not equal to 40, then we could use R as a calculator, or we could add some more arguments to our t.test function. So if I was going to use R as a calculator, I'm going to do my observed mean, 41.28, minus my null value, which is 40, put parentheses around all that, and divide by the standard error, 0.3. And so our test statistic is 4.27. And I always think it's good to kind of guess if you think it's going to be significant or not. And in this case, I know that I'm going to use the t distribution, but I can kind of make my guess based on the normal distribution. So my guess is that this is going to be very significant. And I could use that same kind of idea to do the pt function and put in 4.27 and degrees of freedom equal to 2348. Control enter. And that's going to be everything to the left. So I could either specify lower tail equal false, or I could do 1 minus. It's basically, so the p-value is essentially 0. This here 1 times e to the negative 5 means 0.0000005 zeros. It's basically 0. Or we could modify our t-test, tilde, the number of hours worked last week, data equal GSS. Our alternative is two-sided, and our null value for our mean is 40. And if I control enter, again, I'm going to get a p-value which is 0.001. And so in either case, either by doing R like a calculator or by using the t.test function at the 5% level, we reject the null hypothesis. We have evidence to suggest the true mean number of hours worked is different than 40, and this is because 0.00103 is less than 0.05, and at the 1% level, we also reject the null because 0.00103 is less than 0.01.